Hey students, welcome to class. Today's lesson is going to be finding all roots of polynomial equations. And it's actually kind of a combination of material from lessons 6.5 and 6.6. And we're going to actually be splitting this lesson into two separate days. So there is a warm-up for day 1, and it asks you to factor each expression completely. And just a real quick note, there is an error on one of these questions. So if you'll please look at question number 1 in the warm-up, there should be a y at the end after that 30. So each of these questions ask you to factor it completely. So go ahead and pause the video now and see if you can factor these two polynomials completely. So if you're just tuning in right now, I assume that you were able to try those two warm-up questions. And maybe this is as far as you got. In fact, maybe you didn't even get this far on number 1. You may have just gotten the greatest common factor, but this trinomial that was left over could be broken down again. And so a final factored form for this polynomial would be two binomials and a monomial. Now in number 2, you might have seen right away that you could take out a greatest common factor of the coefficients in the constant term of 3, leaving you with x to the 4th minus x squared minus 8. And then, you know, since we haven't really done a lot of work with these trinomials that start off with something other than x squared, you might not have known where to go from there. But in fact, this is sort of like a quadratic in disguise a little bit. It's going to factor much like the quadratics we factored in chapter 5, although it is a quartic polynomial. Its highest power, its degree is 4. And that's because we can actually think about this x to the 4th power as really being x squared squared. So if you can kind of think about that like that, then we know that each of these binomials would have to start off with an x squared, and then that way when I multiply using FOIL, first two, I'd be multiplying x squared times x squared. That would give me x to the 4th. And then if I think about factors that multiply to give me 8, and oops, and I just noticed that there's a little error in here, so that's okay. That's actually supposed to be a 2 there. I missed that when I was rewriting that. And so then I'm looking for factors of -8 that add up to a -2. That definitely makes things easier. And right away I thought of a -4 and a +2, because -4 times +2 is -8, and those same two numbers add up to give me -2. And so at this point, I mean, if you got that far, I mean, be feeling pretty good. But you actually can even go further. This can be factored again, and in fact that x squared minus 4 is a difference of squares. So I could rewrite this as x minus 2 and x plus 2, and then there's nothing I can do with this x squared plus 2. That there's no sum of squares factoring pattern. Plus 2 is not a perfect square anyway, and so I just have to leave it like that, x squared plus 2. And there are all my factors then. So our learning goals for day 1 are to use factoring to solve polynomial equations. And secondly, to use a graph and synthetic division to identify all real roots of a polynomial equation. In fact, the very last example of the last lesson, 6.4, I showed that, where we maybe used a graph to locate at least one integer value, and then use synthetic division to break the polynomial down to a lower degree and then factor what remained. So we're going to look at more in depth at that method. And then thirdly, we're going to use a graph and synthetic division to find all roots, irrational and imaginary, of a polynomial equation. So we're going to even move out of the real root realm and look at irrational ones and imaginary solutions. So factoring a polynomial equation is one way to find its real zeros or real roots. You can find the roots or solutions of a polynomial equation p of x is equal to 0 by factoring p of x and using the zero product property. So let's real quick look at our multi-step factoring checklist. And this is a review from our factoring unit. And so here are the 5 steps, basically the checklist as you're factoring. Number 1, you always want to put an equation in standard form and set it equal to 0. If possible, you want to then factor out a GCF. Thirdly, count the terms to choose a factoring method. If there's 2 terms, could be a difference of squares. And actually now we could add into this list, or it could be a sum or difference of cubes, because those are 2 new factoring patterns we looked at that work for when you have 2 terms. If you had 3 terms, you could use the easy method or the AC method. And if you have 4 terms, then we can think factor by grouping. The 4th step is to check each factored binomial for difference of squares. So you might get it broken down into some binomial factors, but maybe, as in the warm-up question number 2, one of your binomials or more of your binomial factors might actually be difference of squares. And so you'd want to break those down further. And finally, use the zero product property to find the roots. So example A presents us with one such question where we want to solve the polynomial equation by factoring, and they've already substituted in 0 in for f of x. And so my first step is to check to see if it's in standard form, and standard form would be that descending order of powers, and we've got that here. And so we're on to step 2, which is factor out a GCF. So if I wanted to look for GCF here, what jumps out right away is a 4. I see that each one of the coefficients has a factor of 4, and they all have x's. And the highest power that any one of them could possibly give is the x to the 4th, because that's really as large as that 3rd term can go. So our GCF is going to be 4x to the 4th power. Now if we factor out a 4x to the 4th power out of 4x to the 6th, we're left with x squared. If we factor it out of 4x to the 5th, we are left with an x. And if we factor it out of negative 24x to the 4th, we have minus 6 left over. And so then we can take a look at the trinomial part here. And we can use the easy method just by looking at that 6 here and looking for factors of actually negative 6 that are going to add up to a positive 1, which is that coefficient here of the x. And so right away I'm thinking of 3 and 2, and one of them has to be negative to multiply to give negative 6. And so if I make the 3 the positive 1, and the 2 the negative 1, that means then they'll go ahead and add to a positive 1, but still multiply to negative 6. And so then I look at my 2 binomials. There's nothing I can do to break either one of those down. And so now I'm at the point where I can go ahead and solve these. And so when I solve, I look at each one of these pieces and I set it equal to 0. And by doing that and using the zero product property, I can find my zeros or my solutions. So let's see, what makes 4x to the 4th power equal to 0? Well, there's only one number that I could plug in for x that would make that 0, and that actually is 0. If I look at the x plus 3 piece, well, I know that x must be negative 3 to make that quantity equal to 0. And for this next one, x must be positive 2. And so my 3 solutions are 0, negative 3, and 2. And so that does it for that example. Let's move on. Let's take a look at example B. So our first step was to make sure that our polynomial is in standard form. Well, it certainly is not in standard form because we have to have everything on the same side and 0 on the other. That's the first thing. And we also want it in descending order of power. So I'm going to go ahead and I'm going to subtract 26x squared from both sides. And when I do, that leaves me with x to the 4th minus 26x squared plus 25, and that's going to be equal to 0. Well, this particular one is one of those kind of like fake quadratics that I talked about in the warm-up. See, we actually have a power of 4 on our x term, and so actually I know that each of the binomial factors are going to have to start off with an x squared, because x squared times x squared is x to the 4th. And then I think about looking at this 25 and think, what factors of 25 would multiply to give 25 and add to give negative 26? And it doesn't kind of come to me right away because I'm kind of thinking of positive factors, but if they were both negative, like if I had negative 25 and negative 1, they would multiply to give me this positive 25, and they would add to give me this negative 26 that I need. And so that's what I'm going to use. I'm going to use the x squared minus 25 and the x squared minus 1. Well, then it turns out that each one of these binomials actually can be factored further because they're both difference of squares. This first one, x squared minus 25, can be rewritten as nearly identical binomials, only differing by the sign. One's a plus and one's a minus. And the factors come from square rooting the x squared and the 25. So they're x plus 5, x minus 5. And I can do the exact same thing with the x squared minus 1 because they as well are both perfect squares. So I'm going to get an x plus 1 and an x minus 1. And so all that's left is to use the zero product property then to find the solutions. So if I take a look at each one of those and set them equal to 0, then my solutions are x equals 5, negative 5, 1, and negative 1. And so I've got 4 solutions, which makes sense. It's consistent with what's possible when we have a degree 4 equation that we're solving, that we anticipate that we could potentially get 4 real solutions. Okay, so we've got that one under our belt. Let's try one more. Now this time we again have to get standard form. So we want to bring this 50 over to be with the other terms, and that'll put it in standard form. And so this is what it looks like when I get it in the descending order of powers and everything on the same side. And I've got a 4-term polynomial. So I looked first of all to see if there's a GCF, and there's not. But then I see that this is a 4-term polynomial. So I think right away, how about factoring by grouping? Let's see if that's possible. And so I'm going to go ahead and look at that first pairing, the first two. Take out my GCF. Well, I can see I could take an x squared out of both terms. And when I do, I'm left with an x minus 2. And looking at the second pairing, the leading term is a negative 25. And so I want to take out a negative, and then the GCF of the 25 and the 50 is 25, so I'm actually going to take out negative 25, which is going to leave me with an x and then a minus 2. And just as we wanted to have happen, we ended up with a binomial that is common in both. That's our common binomial factor. And that means that the two numbers out in front produce one of my binomial factors. That's x squared minus 25. And the other one is x minus 2. And then we have one more breakdown we can make because this one is a difference of squares. And so I can rewrite that as x minus 5, x plus 5, and then of course we have the x minus 2 as well. And that's going to result in my solutions being, let's see, that's going to give me solutions of a 5, a negative 5, and a 2. And again, that makes sense. I got 3 solutions, which is as many as I possibly could get, being that this is a degree 3. Okay, so now let's look at another example. Now this time, we're asked to identify all of the real roots of a polynomial equation. And we're presented this time with this polynomial that is a 4-term polynomial. So I think right away about this whole factor by grouping thing. I looked to see if there was a GCF, it's in standard form, and I actually kind of just scoped out this whole idea of being able to break it down and factor by grouping, and I realized that it's not something that I could factor. I'm not going to get a common binomial factor when I factor by grouping. So this is not going to be an option here to just straight factor to solve. And so what I decided to do is I wanted to graph this. So I went ahead and put this in my calculator and showed a little snapshot of what the graph looks like. And when I went to the table, oh, and by the way, I could see that there were two solutions that I could see that were real. And they were right here. There was one here and one here. Now, unfortunately, until I actually graphed this, I did not realize that it didn't actually have an integer solution. So neither one of these that are shown on the graph turn out to be crossing at an integer value. And so that was an error on our part, and mainly we'll be looking at ones that we can find one of the integer values in the table. So in this case, I'm just going to tell you that one of these solutions right here turns out to be at -1/2. And so we know that that one solution that we know from the table is this -1/2, and we can use this to go through that process of synthetic division, then to break down this cubic polynomial, break it down to a quadratic polynomial that I might be able to factor, or if not, I at least have that quadratic formula that I know can always be used to solve quadratic equations. So again, as you see here in the directions, it says use the calculator to find or to graph the polynomial, and then use the table function and graph to find an integer x-intercept. And of course that didn't happen here. Oops, and this was our x-intercept. But typically it will be, yes, it will usually be an integer that we'll be finding. So step 2 is then to use synthetic division to divide the integer, well, in this case the fraction that we found, into 2x cubed minus 3x squared minus 10x minus 4. And so I went ahead and took the coefficients, including the signs, and I set up a little synthetic division format here. And we're going to just kind of work through that process. So, and you can do this. It doesn't matter that it's not an integer. That's fine. So you bring down the first term, and it's a 2. And then we're going to multiply the -1/2 by the 2, and we're going to add it to this next term. So -1/2 times 2 is going to be -1. Add those two terms together, we get -4. Now we're going to multiply again. And so we're going to go over here, we're going to multiply the -1/2 by the -4, put it right underneath the next column, and so a -1/2 and a -4 is a +2. Add those two together, and we get a -8, and we're going to multiply again, and this time it's -1/2 times -8, and that turns out to be a +4, which when I add it to the -4 in the column right above it, I get a 0, which of course is what I hoped was going to happen. I anticipated happen because I know that -1/2 actually is one of the solutions, so we should get a remainder of 0. And so the resulting polynomial that's left over is 1 degree lower than the original, and that means that this 2 really is the coefficient of the x squared term, and then -4, we drop down to the next power, that's an x, and then -8. Now, in most cases, it might be worthwhile going through the process to see if then you could factor this 2x squared minus 4x minus 8. But I'll tell you, this one is not factorable. And so we're going to go straight to using the quadratic formula. So see if I can remember the quadratic formula. Remember, it's x equals opposite of b plus or minus the square root of b squared minus 4ac, and all of that over 2a. And I'm going to go ahead and work that process here. So let's see, the opposite of b. Well, the b is -4, so the opposite of that would be 4. Plus or minus the square root of -4 squared is 16. minus 4 times a, which 4 times 2 is 8, times negative 8 is negative 64. And that's all over 2 times a, and the a is 2, which means the denominator is 4. So that means this is 4 plus or minus the square root of 80 divided by 4. So if I were to break down that 80 into its perfect square factor, I could take out a 16. So I could rewrite that as the square root of 16 times the square root of 5, which means that's 4 plus or minus. The square root of 16 is 4, and square root of 5, that's what square root of 80 reduces to, is 4 square root of 5, and then all over 4. And so then we can break that down. We can give both the 4 and the 4 square root of 5 the denominator of 4, which then cancels out and turns into 1 plus or minus the square root of 5. And those then are the other two solutions that go along with this negative a half. So if I want to list all the solutions, my solutions are x is equal to negative a half, and then also 1 plus or minus the square root of 5. So there's 1 plus the square root of 5 and 1 minus the square root of 5. And that gives me my three solutions, my three possible solutions for this cubic equation. Let's go ahead and turn the page. Now this example, I scoped it out ahead of time again, and this one is another one that there's just not an integer solution listed in the table. There's not an integer solution, and so we're going to just go ahead and cross this one off. We've got plenty other examples to look at, so we're going to skip this one because there is no integer solution, and move on to the next example. So let's take a look at this one. So it says solve the polynomial equation by finding all of its roots. Well, this time I'm looking at a polynomial that's a quartic equation. It's got 5 terms. Well, we haven't talked at all about factoring things with 5 terms. And so this is one of those perfect candidates for using the graph to see if we can find some of the solutions. So I went ahead and I graphed it, and again I included the picture here. And so right away I looked at the table and I was able to locate an integer solutions right off the bat. It was this right here at -1. And so I used the calculator to graph the polynomial. I used the table function and graph to find an integer x-intercept, and it was x is equal to -1. So my next step is to go ahead and use that -1 and the synthetic division process and break this 5-term polynomial down into one that instead of being a quartic equation will be a cubic equation. It will be one less term. So instead of having 5, I have 4, and there's the potential then for the factor by grouping method. So we go ahead and take the coefficients of, we got the numbers out in front of the variables and the constant term. So we're going to transfer those over into our synthetic format, and it'll look like this: 1, -3, 5, -27, and -36. And we're going to go ahead and start that synthetic process by bringing down the first term, multiplying, and putting that right into the next column. So -1 times 1 is -1. I'm going to add those together. I get -4. I'm going to multiply again. So this time -1 times -4, which is +4. Those add together to give me 9. Another multiplication. We've got a -1 times the 9, which is -9. Add those together, we get a -36. And then the final multiplication is going to be the -1 times the -36, which gives us a +36. Add those two together and we get a 0, which again is not surprising. We should be getting a 0 for a remainder if in fact that number, -1, was a solution. And so what that means is the remaining polynomial after that synthetic process is the next power down, and so that will be x, I should say 1x cubed minus 4x squared plus 9x minus 36. So this time we have one that we could give a shot with this factor by grouping method. So I'm going to go ahead and split these down the middle, look at the first pairing and see what I can do. Well, I could take an x squared out of both. So when I do that, see if I can fit this all in here. Take out the x squared, that leaves me with an x minus 4, and then out of the 9x and the minus 36, I'm going to take out a 9, and that leaves me with x minus 4. So there's that common binomial that I was hoping to get. And that means that the factored form of this is going to be x squared plus 9 times x minus 4. Now x squared plus 9 is a sum of squares. So that means that I can't break that down into smaller binomials, but it doesn't mean that I can't solve though. So I can see right away that one of the other solutions is this 4. So I have solutions. The first one that I was able to get from the table, which was the -1. And I see from this binomial, x minus 4, that one of the solutions would have to be 4. And then what this other one tells me, this x squared plus 9, if I were to set that one equal to 0, or x squared plus 9 equals 0, and subtract 9 from both sides, I would get x squared equals -9. And I know that if I took the square root of both sides, that the square root of -9 is plus or minus 3i. So those are my other two solutions, positive 3i and negative 3i. And so this time I was able to come up with 4 solutions, which goes along with the fact that this was a quartic equation. But this time I had 2 real and 2 non-real. And so again, to make this whole process clear, basically you look to see if a polynomial is something that you can factor right off the bat. If you can't, then you need to graph the function, see if you can find one or more integer solutions from the table. Take one of those integer solutions and break your original polynomial down to a lower degree polynomial by just simply going through the synthetic process. And then take a look at the remaining polynomial and see what you can do from there. You might then be able to factor it. It might be broken down into something you could use the quadratic formula on, but then at least you have some options. Whereas at the beginning, you would, with a 5-term polynomial like this, we have nowhere to go. So graphing really opens up some options for us by providing us with one or more of the integer solutions. So let's go ahead and turn the page. So here is one I would like to assign as a you try question. So I have graphed this function here, but it's a good idea. Well, you should, because I don't have the table here. You should go ahead and get out your calculator, graph this polynomial, look at the table, and see if you can identify one of these 2 places where you can clearly see this crosses the x-axis, to see if you can identify one of the integer solutions so that you can go to step 2 and use synthetic division to divide the integer that you found into the original polynomial to break that down, similarly to the one we did in the prior example. So we're currently starting off with a 5-term polynomial. We don't know how to factor that, but see if you can break it down using synthetic by identifying one integer solution. And then see if you can factor what remains with factor by grouping. Go ahead and pause the video now. Okay, so there really were 2 options here. 2 integer solutions showed in the table, a -5 and 1. I chose to use 1. You could have used the -5. You'd end up with the same final solutions, but the process would look a little different. So, if you chose 1, you can follow the logic of my work and see where I ended up with those 4 solutions of 1, -5, the 2 that you could see in the table, and then 2i and -2i that I was able to find by solving for the binomial x squared plus 4 using the zero product property. So go ahead and take a few moments and look through the answers to this. And just remember, if you have any questions, any things you need clarifying, when we meet in class, we certainly will have opportunities to talk about these, because these methods that we're using are pretty sophisticated methods, and certainly there will be some questions that arise. So I'll look forward to taking those questions when I see you in class.